Hi everybody, welcome back. Well, I got an awful lot of comments from the last video saying that a lot of you are very interested in seeing how to implement a speaker protect circuit in an amplifier that does not have one. And so I thought I would go ahead and do that for you. And we're going to break this up a little bit. You know, the beginning of the video, we're going to kind of talk about what speaker protection is, or what an amplifier protect circuit is, because there's several different types of circuits and they do different things. So we're going to explain what those are in the beginning here. Then we're going to go through and look at a couple example circuits of them and kind of how they work. And then last but not least, what we're going to do is we're going to build actually this little kit here that I purchased on eBay. It was very inexpensive. And then we're going to talk a little bit about this a little more fancy version of the kit that has a few more features on it. And we'll do a little solder and chat while we put this together, and then we will implement it into our little Kenwood KR710 and then see how it works. So if that sounds interesting to you, stay tuned, and that's what we'll be doing in this video. Okay, let's start by going over some of the different types of protection circuits that exist. I actually got organized this time. How about that? And wrote some stuff down, you know, because whenever I try to go off the top of my head, it usually ends in disaster. You know, sometimes the wheel's turning, but the hamster's dead. I've said that before. Now, some of you are gonna come out on the comments. Maybe you have dementia. You know, no, I don't have dementia. I do have messing with you. Anyhow, let's get on with this. So there are some different types of protection circuits, and they go from simple to more complex. The most simple one is called the delay relay, and all it really is a relay that you put between the speaker terminals and the output of the amplifier, and you put a little delay circuit on the coil, so that when you flip the switch on to the amplifier, it'll wait a few seconds and then pull in the relay and connect the speakers. Now, why would you want that? Well, the main reason for that, if any of you saw the video series I did on the ADCOM, the GFA 585, that is a good example. When that amplifier turns on, and as the capacitors are charging up and all the power supplies are settling, you get this really hard, loud pop out to the speakers. And it's totally normal. That's how it's designed, because there's no speaker protect relay circuit in that. So the speakers are directly connected to the output transistors even as they are powering up and the capacitors are charging. So you get that big, huge thump. So what this does is it just holds the speakers, it disconnects them until the amplifier stabilizes for the power supply, which usually only takes a couple of seconds. And then it connects the speakers so you don't hear that loud pop. And that's really all this does. It does nothing to protect the speakers from anything else. And if the output transistors are shorted after that short delay, all it's going to do is connect your speakers to that shorted output and blow your speakers. So this is really not a full protection circuit as per se. All right. Now, the really, really inexpensive, simple protect circuits, as they call it, that you buy on eBay and so forth, you have to watch, because some of them are simply just this. It's just a time delayed relay circuit. The next level of protect circuit is the DC offset protection. Now, this is a little different. It also has the delayed on, so the relay won't come on for a couple of seconds after you turn it on. But there is also a little sensing circuit. When it sees, most of them are around 700 millivolts, but if it sees more than about 700 millivolts or so, and that will vary depending on the circuit or how it's adjusted, it will not allow the speaker relay to pull in. And if at any time while the amplifier is powered up, the DC offset voltage at the speakers goes above that threshold, it drops out the relay. So the worst that can possibly happen is for that split second while the relay is dropping out and the circuit is acting, just for that split second do you get that DC offset onto your speakers. So the chances of you shorting and blowing out your speakers is greatly, greatly reduced by this circuit. This is the very most common circuit that you'll see in amplifiers that have a protect circuit. So when you hear people say about the protect relay just came in or the protect relay is not coming in, this is what they're usually talking about, is this offset, this DC offset protection. Some of the fancier ones will also have a single pole double throw relay contact, and the normally closed contact, which is the one that'll be closed when there's no power on the coil of the relay, that one will be connected to ground. So what ends up happening is when the relay disconnects the speakers from the amplifier, it will connect the speakers to ground and kind of short them out. And that will greatly reduce the arc flash that you'll get on the contacts as they're disconnecting. It actually helps that, and it prevents the speakers from seeing a big spike when it disconnects. So that's something you'll see in some of the higher end DC offset protect circuits. The next one you don't see quite as often. It's called AC sense, and all it is an additional circuit, and of course it'll have these two features as well. This is another feature that'll be on there, and that AC sense is just there to monitor when you turn the power off. So if you shut the power to the amplifier off, what it's going to do, it is very quickly going to shut down or break the relay contacts from the speakers. And the main reason for that is the same reason that the delayed on is in there. Some amplifiers will give you that big popping noise when the amplifier turns off, as well as the capacitors discharge unevenly, and you'll get like a warbly kind of low bass popping sound in the speakers. The AC sense circuit will ensure that the relay will drop out before that happens. So as soon as you hit the power switch to the amplifier, it senses that and it quickly drops the relay out. So that's AC sense. The next one is where it gets a little more complex. And we're going to look at some schematics of some of these things here when we're done. The next one is an overcurrent or overload protect circuit. And usually consists of a couple of transistors that are situated in the driver section of the amplifier, and they monitor those emitter resistors. You know how you have those big ceramic resistors? If you remember on this Kenwood that we're working on, if you look in here, you have these ceramic resistors that won't come into focus right now. There you go. And these are connected to the emitters usually, or the collectors of the output transistors. It actually monitors the voltage drop across that. And from that, you can calculate the actual current flowing through the circuit, which is theoretically also flowing through the speakers. And when you have an overcurrent situation, what will happen is those two transistors will begin to short out or attenuate the signal, the drive signal, your audio signal going into the bases of your driver transistors. So essentially what it's going to do is it's going to throttle back the amplifier so that it can't go into an overcurrent or an overload situation. That's going to protect the speakers from excessive clipping, and like a hard clipping, and it's also going to protect your output transistors from overheating from too much current draw. And this all happens very quickly as the amplifier is acting, and if it happens quickly enough, you don't even hardly hear it unless you're really turning the amplifier up really loud, and then it'll just kind of sound a little bit like distortion. So that's what that's for. Amplifiers that have this, you have a lot less chance of blowing your output transistors. So this is a really good circuit to have, but again, you usually only see this on the higher end stereos. The last one we worked on was that had this, I think, on the videos. was the Marantz 2240. And even though it's just a small 40 watt amplifier, it isn't their real high end one, it actually had this circuit in it as well as all these other ones. And that's why that is such a bulletproof amplifier. You know, you can't really kill that amp. It's very reliable, and it's a really good amplifier to use on your bench for test, and beyond being just a really fantastic sounding amplifier. So that's mainly what a Protect circuit is and what it does. There are different levels of them, and not every amplifier has all of these. Now, we'll talk about some of the ways they implement this and look at some schematics here in a minute, but I also thought you might be interested in seeing a couple of other circuits that they're not really what I would call Protect circuits, but they're also circuits that kind of protect the amplifier in some other ways. The first one is called the overdrive or distortion limiting circuit. That's a name I gave to it. Different amplifier companies or different manufacturers will have a different name for the circuit. But essentially what it's doing is it's similar to the overload protect. But what it does is it just monitors if you're going to drive too much signal into your amplifier, what's going to drive it into hard clipping and cause it to distort. This will actually reduce the actual gain of your driver circuit. It won't just squelch out the signal at the base of the transistor, but it will actually reduce the gain of that stage so that it can't, and it does it dynamically, you know, as the amplifier is driving. So it's happening very quickly. Those ones, you can crank the volume way up and really drive the amp hard, but it won't distort. It'll just kind of throttle it back, and it just won't let the volume get any louder than it can get without distorting. So these are really cool. This circuit is used, one of the earliest implementations, and correct me if any of you know of any other circuits. I'm sure there's other companies that have done this as well. But Macintosh did this in some of their earlier transistor amplifiers. The 2100, the MC 2100 that we did, had the overcurrent overload protect. They called it the Sentinel circuit. But some of the later models right after that also had this. And I forget what they call it. I'd have to look it up. But they have a formal name they use for it. And they have both of these circuits in their amplifiers. Very, very cool. That's why those things were so clean, and you just could, you know, they were so bulletproof. You just couldn't hurt them. They ran and ran and ran, and, you know, good amplifiers. So it kind of works like an auto gain control. If you know, you've heard of the AGC or the AVC in little AM radios and things. It's kind of the same idea. You're adjusting the gain to prevent, you know, overdriving something. All right, the next circuit is called a soft start power circuit, and you've seen these before. I think I went into some greater detail on how it works on the Pioneer SX 1050 videos that I did, and I also think I got into this a little bit into the Marantz 2500 video that I did, where we kind of got a little more in depth how this works. But really all you're doing is you're taking a really big high wattage, low resistance ceramic resistor or an inrush thermistor, and you're putting it right in series between the rectifier circuit and your big main filter capacitors, these big guys right here. In some of the, you know, the higher end, the higher wattage amplifiers, you know, the 120, 150, 200 watt amps, they have these great big, you know, soda can sized capacitors. And the inrush current, for instance, the SX 1050, the inrush current, when you first turn that on, if you did not have a current limiting circuit in there, is about 280 amps. Now remember, the average mains mains circuit in the United States for 120 volts is either 15 amp or 20 amp. And you know, over in Europe, you guys can speak for what yours is. I think it's somewhere around 13 amps at 240 volts. Correct me in that. But the bottom line is it's a lot less than 280 amps. And so And that's only for a split second, but quite often it's enough to pop the breaker in your house. It can actually happen in your breaker box, or blow the fuse, and also puts incredible stress on the contacts of the power switch of the amplifier. So what we want to do is we want to limit that. So what they do is they put that resistor in there, and the resistor absorbs the current and limits it. Kind of like our dim bulb tester does when we're putting something on the bench to test it through that light bulb. It does the same thing. It's just it allows the capacitor to charge up more slowly. When you have that resistor in series with the capacitor, you have an RC time constant. So you can regulate the current at the expense of time. It's going to take the cap a little longer to charge. But we don't care about that. You only need it to be on there for a second or two. And then a relay will come in and just short out that resistor and allow the full power from the power supply transformer to get into the capacitors. So that's how that works. You won't see this on small amplifiers because the capacitors aren't big enough to have a problem with the inrush current. Usually the wiring and things like that in the transformer itself will limit the current enough that it really doesn't matter. But with these great big power supplies, you really need this. So that's what that is. I think I have one more thing here. I do. And the last thing is something that I've gotten a lot of questions about in the comments section. So I thought I would address it. When I did the Pioneer, I think it was the SA9800 amplifier video, it had a special kind of bias circuit. And we know when we adjust the bias on an output section of an amplifier, what you're doing is you're putting a little bit of idle current onto the amplifier, and you're switching it on just above that, you know, that forward voltage drop of the transistor. So the transistor is actually turned on just a little bit. And that eliminates the crossover distortion. And you can go back on videos and look what all those terms mean if you don't already know. But Pioneer experimented with this, and I'm not sure if other companies did as well. I'm sure they did. But what they do is they have a two-stage bias circuit. So instead of just setting your idle current bias, you set your standard idle current bias, just like you would on a normal amplifier. But then what you're going to do is you have a second bias circuit. Let me expand this a little bit. You have a second bias circuit that's adjusted just a little bit above that. And what's going to happen is when the amplifier is going through its positive and negative half cycle, so you have a like in your output section of your amplifier, here's one right here, here's your output section. As this is your positive DC rail and your negative DC rail, and for the positive half cycle of your sound, this transistor's turned on, and as this turns on, this will drop down through that little idle current voltage, and this transistor will completely switch off. And then this one will handle the whole load for that positive half cycle. When you get back down to 0 volts, just above 0 volts, this will kick back on and start to conduct again. And then as you go to the negative half cycle, this transistor will handle the load, and when you get down below that little bias setting, this transistor will shut off completely. And so there's just a little tiny period of time where both transistors will be turned on at the same time, and it's right in that bias area. But at any given time above or below that, one transistor will be off and the other will be on. What the zero switching circuit does is when you get past that bias level, and this transistor is handling the load, let's say for instance, there's a hold-on circuit that will just keep a little bit of bias on this transistor so it doesn't totally turn off until this guy comes back down to 0 crossing, and this one starts to turn on. And apparently that will help to reduce the switching noise of the transistor, turning on and off. So it's supposed to, in theory, reduce distortion even beyond what a standard bias circuit does. If there were no bias circuit on here at all, you would have this notch where, like, this period of time until the transistor turns on from 0 volts up into that forward voltage drop of, half a volt or so. on both sides, and that's called notch distortion or crossover distortion. So that's what the bias circuit does. But beyond that, they're saying that the transistor will never turn off at all. Even when this is handling the whole load, this is kind of sitting here at a little idle point so that it will pick up, you know, to the bias point once this goes down through zero crossing. Does it make a huge difference? I don't know. I mean, I have some pretty sensitive distortion equipment, and yes, that SA9800 has really low distortion, but I don't know. I mean, you know, it's up to your ears whether you think that it makes that big a difference or not. I'll leave it at that. All right, now that we know what a speaker protect circuit is, why don't we look at a couple examples. The first one I'm looking at is one that I drew up on KiCad, and it's almost, not quite, but very close to just a knockoff of how these little circuits are designed. And I don't know that this one is this doesn't come with a schematic. It just comes with the wiring, how to put the components in. But this is very similar to what we have here. I'll just put it that way. So this is not something I invented. It's just a circuit that's out there, and I just drew it up and kind of changed a few things on it, but it's for all intents and purposes the same circuit. And the main thing I want to kind of show you is how this simple little circuit can sense DC versus AC. Because remember, if you have a big AC signal in there, you know, the voltage is going to go up and down. We don't want to shut the relay off. We want it to stay on. So what we need to know is we have to see if there is voltage there that's unchanging for a specific period of time. And it's actually pretty simple to do that, believe it or not. If you look here, here's your left and right channels. And these are going to be connected directly to your speaker terminals. So you can see they're connected right to the speaker terminals. And you have this 10K resistor, and that just raises the impedance and lowers, you know, so there's basically with a 10K resistor, this is not having much influence on your amplifier or your speakers. And it's just a low wattage 10K resistor. And what you're doing is as the signal goes through this 10K resistor, it begins to charge this non-polarized capacitor. Now, a lot of them, they'll either have a non-polar capacitor or they'll have two polarized electrolytics back to back like this to make it a non-polarized cap, because you are going to have AC voltage here. If you have a complementary amplifier, push-pull AB, it will put a positive going voltage and a negative going voltage. If you just have one of those ones like that Scott amplifier that we just did in a couple videos ago that has the capacitor driven output, that will never switch polarity. And I explained how that works in one of my videos about different amplifier classes and so forth. So you can go back and watch that if you want. But anyway, what's going to happen is this is going to act like two different things. Number one, it's going to act like an RC time constant. So, you know, as you apply voltage across this 10 ohm resistor or 10K resistor, it will charge this capacitor. And, you know, depending on how both channels are operating, so this is monitoring both channels. If either channel has a problem, it'll charge this capacitor. It also acts like a low pass filter. So any high frequency here is going to be shunted to ground through this capacitor right here. So the only thing that'll get through here is actual pure DC after a certain period of time. Now that DC voltage is going to go through this little bridge rectifier. And this bridge is here for the purpose of, we don't know whether we're monitoring the positive half cycle or the negative half cycle where our volt, so it depends on which output transistor shorts as to whether you'll have a positive voltage offset or a negative voltage offset. Because remember, we're trying to see if a transistor shorted and we're getting DC voltage out on our speakers. So all this bridge rectifier does is it just steers that in one direction, so that it doesn't matter which way it goes, you're going to get the same signal through here. And yes, I don't have this in backwards, okay? This is connected to the positive down here, and this is connected to the negative up here, and then your ground and your input are connected to the AC of the bridge rectifier. Now, so what we're going to have is a DC voltage between the base and emitter of this transistor. So you know me, whenever you have a circuit that looks a little bit different than what you're used to seeing, I like to redraw the circuit to make it make more sense to me. And in redrawing it, it helps me to understand more about how it works. So that's what I did. I just took a piece of scrap paper and just scribbled down a little redrawing of the first stage of this protect circuit. So when you look at the way this really works, you have this 10K resistor, and of course it's being fed across this high pass or this low pass filter. And so any high frequency component already is going to be shunted to ground through this capacitor right here. Just think of this as a single capacitor because it's just a non-polarized. And this little bridge, which is kind of, I drew it in the wrong place here. It should actually be drawn down here. Sorry about that. It's just ensuring that the current that flows through this circuit over here is always flowing in the correct direction, because of course transistors won't work in reverse bias. So that's all this bridge does right here. And if you redraw it, essentially what's happening is this bridge is ensuring that this 10K resistor here, the signal coming through here, always is flowing in the same direction, and it goes through this bridge and across this 10K resistor, which goes through this diode here and to ground, and it forms a voltage divider. So you can see that voltage divider right here, and it's at the base of the transistor. Now, in addition to that, I'm sorry, this end goes through this diode. The emitter goes through this diode. So you actually have a couple of diode drops, which is the transistor and then two of the diodes at any given time. So you're going to have maybe, what, 1.5 to 2 volts, something like that. Okay. And what that's going to do is that's going to affect the trigger of this transistor. When this transistor turns on, it's actually going to begin to short out this circuit or reduce the resistance of this circuit, let's say. And if you look up here, there's a 12 volt signal, and that's right here, 12 volt source. It goes through this 250K adjustment pot and then this 10K, and then it goes in series with this 39K to make a voltage divider at this point. So this voltage divider is going to kind of set up a pre-charge. So with no signal here, this is going to charge up. This capacitor acts like an RC time constant, and there's enough current here, even with this bypass resistor, to charge this cap up, at which point you have a high voltage here, and that high signal turns on the base of this to turn on the relays. So this 220 microfarad capacitor is your turn on delay. So this is the delay that it will take for this to turn on. If this doesn't charge up, this can't turn the transistors or the relays on. Okay. Now, as you begin to put a DC level through here, something that gets through this high pass filter, or through this low pass filter, I keep calling it high pass, through this low pass filter, it is going to begin to turn this transistor on, which is going to change how fast this can discharge this 220 microfarad capacitor until eventually this voltage drops too low to keep these two transistors turned on. And as soon as that happens, the relay drops out. Now when the relay drops out, you lose signal. When you lose signal, it's going to sit here and wait for this to go back down. So as soon as you don't have DC, so let's say that you don't have a shorted transistor, let's say you were just driving into hard clipping, as soon as you do that and you turn the volume down, this is going to begin to reset. This will turn back off, this will begin to charge this back up, and after it goes through its time constant, this turns back on and the relay pulls back in. If you have a shorted transistor though in your output, this is going to stay turned on, this is going to stay low, and it's going to prevent these from turning on. That's how this little circuit works in a nutshell. Now in this one, they're also using the circuit, in line for this transistor. They're using that to drive the LED. This is actually just like a little small signal driver transistor. And then this drives, and not only will this light the LED, but this will also limit your current. And then this allows the big transistor to turn on. And this is actually the transistor that allows the coils to go from 12 volts through the coils through here and into ground. And then you have your freewheel diode, okay, and that just keeps the that back EMF from these coils from shorting out the transistors when they come, when they drop out. So that's all there. It's a really simple circuit, but it can be kind of confusing when you look at it at first. But really it's in stages. And first of all, you want to filter out anything that's not AC and just allow the DC or near DC to pass. By changing this value here, I can change what frequency it'll trip this. So for instance, if I decrease these capacitors in value, so I make less microfarads, it's going to make this turn on more easily. So I can have it that, at low frequencies or subsonic frequencies, it's not going to allow that. It'll trip the protect circuit. Conversely, I can also make it allow a lot more DC to get through here before it'll trip. So some amplifiers, when you get below 10 or 20 hertz, it'll trip the protect circuit because it sees too long of a delay in that frequency. But you can increase this value a little bit and it'll allow that. If you go back to my Sansui 9090 video, I actually did that, because that amplifier, when you would drive it, subsonic frequencies, like right just around 20 hertz or a little bit below, the frequencies you can feel with a big speaker, it would very easily trip this circuit, and without even having, real high current. So I just changed that value a little bit, and it allowed the amplifier to produce those subsonics. Now, of course, that's not good when you're using turntables. You would have to turn down your bass or your loudness control or whatever. But it allowed you to get those really low frequencies that you can get with, digital audio that we have today. Interesting stuff. Okay. So now that we looked at that, let's look at a real-world example of a protect circuit. This is the protect circuit out of I think this is out of that Marantz 2240 that we did, and I just kind of cropped out that section of the schematic. And if you look in here, you have these two diodes coming from your power transformer, and these are rectifying that AC into DC, which is going across here and being filtered by this 10 microfarad. Notice they don't have a really high capacitance here. It is like that for a reason, because this not only acts as the power supply to power your protect circuit, but it's also an AC sense circuit. So As soon as you lose your AC power from your mains transformer there, coming from the mains, this will discharge very rapidly and you lose power to your relay and the relay drops out instantly. So here again, that's your AC sense. So this will stop the amplifier from getting that popping noise when you shut the amplifier off. Now, if you go down here, you have your amplifier left and right signals coming in, and they're going through these 5.6K resistors. And I'm not showing all of the circuit. There's some other things in the amplifier, but these are pretty much your outputs. And they come through, instead of 10K resistors, they're 5.6K. And they go up and they divide with this circuit right here. And this is your DC detect and low pass filter. And I put these little notes on here so you can see them. And here's your little filter circuit. It's 47 microfarads on this. Okay, remember we had a 220 microfarad. And if you notice, it's already a DC signal by the time it comes in here. So that's why this is a polarized electrolytic. Like I said, there's some other stuff back here that does the rectifying for you. This is that same circuit. Here's your transistor. Here's your delay capacitor. And this is your reset and trip delay. So what this is going to do is, once again, it's going to have to charge up from this voltage divider here, just like what we had with this voltage divider here, we have here. And then we have this transistor the same way that affects that can actually reduce the voltage here. And when that voltage gets below 1.3 volts at the base, this transistor can no longer turn on, which can no longer turn on this larger transistor to bring the coil of your relay to ground. Same circuit. Now, instead of having two separate relays and they're not using the grounds, they're just using one relay to take care of both. And you can do that. This is a double pole, double throw instead of a single pole, double throw. And again, they could take this and connect it to ground, so that, but they would have to reverse the leads. In other words, if you put the speaker lead to here, and then you connected this one to ground and this one to this point, you could actually have it ground out the speaker when the amplifier goes into protect. So that would be a little mod that if you wanted to do, you could, but I think you'd have to cut traces on the board. I wouldn't want to do that. Anyway, very simple circuit. Now our next circuit we're going to look at is this little green section. I've kind of cut out just the power amp section of that Marantz amplifier, I believe is what this is. And again, you can see this little circuit here, and you notice there's two transistors here with these little diodes, and you have these little resistors here. One of them's 200 ohms, one's 360 ohms, raising the bases above your common point of the output section. So this whole line, this is what's driving your speakers right in here. This goes through this little filter network and goes straight to your speaker terminals right here. So if you look, that's where we're at right now. You can see there's a little circuit that's wired across these resistors here and across these R733 and 732. If you look, they go directly from here, and this is on the emitter of the resistor, or of the output transistor, through this dropping resistor and then this little snubber, and then it goes through here, and you have this little divider network here, and across this to here. And what this is doing is it's making the base pretty much monitor the voltage drop across this ceramic resistor. And this would represent those ceramic resistors I just showed you on the Kenwood amp. And if the voltage drop gets too high here, these things are going to begin to turn on. And as they turn on, this diode right here is connected to the driver. Here's your driver. Here's the base of the driver. Here's your input signal to the driver. You can see what it's going to do. It's going to bypass it straight to here. So it's going to squelch out that signal at that base. So if you have an overcurrent, it's going to throttle the input of this and not allow this thing to drive that hard. Now you'll get what looks like hard clipping. You'll get like it's clipping, but it's not the type of clipping that is overdriving the amplifier. It's clipping because it's actually turning the signal off for that period of time to prevent an overcurrent situation. So that's what this is. This is different from what that DC level protect circuit does. And there's different ways of implementing it. So if you look over here, here's the Macintosh MC2100. And you can see in this red section, very similar. There's your diodes, there's the drivers, there's the bases to the drivers, here's your little divider network, here's the bases of your overcurrent protect circuit. But now in this one, they're actually using Darlington transistors for higher gain. It's because that's what they need for this particular circuit to make it. That's just the way they designed it. But it does the same thing as what we just looked at. And even if we go up to the huge Pioneer SX 1980, which is just a really complicated amplifier, same thing here, but instead of using Darlington transistors, they just use 2 transistors like this. And, 2 separate ones instead of 1 Darlington. And same thing though, there's your diode. There's the base of your driver circuit. Here's your divider resistors. There's your center point from your speakers right here. All the same stuff. Just a little bit more complex, but it's the same idea, the way they're doing it.